Hello, ladies and gentlemen. This is MTS 102. The course title is Introductory Mathematics 2. Today we are moving to Study Section 6. Study Section 6, where we have the methods of integration. Methods of integration. Here we have the objectives of the section. That is, on completing this section, you should be able to understand methods of integration and also solve some example on each unit. Now, these are the contents under the methods of integration. We have integration of polynomials, integration of functions, integration of trigonometric functions, integration by substitution, and also integration by parts. All these we are going to be looking at it one after the other. Here we have the introduction to the section. That is, many integration formulas can be derived directly from their corresponding derivative formulas, while other integration problems require more work. So, here is the learning activities, the learning outcomes, so which we have mentioned under the course objectives. So, we'll be looking at it now, one after the other. Here we have the integration of polynomials. Integration of polynomials, which I believe you all know what is called polynomials. That is when you have a function in this form. That is where we have y equal to ax raised to the power of n. That is the general form of it. The general form of a polynomial. So we now want to integrate it. So if you are to integrate the function y equal to ax raised to the power of n, then we have the integral sign there. So take the integral of the both sides, where we have y the s, and what is y? Y is ax raised to the power of n. Then take the integral of it, that is integral ax raised to the power of n ds. So how do we integrate this? You know the coefficient of s there is a. Then the s there is the base value and is raised to the power of n plus 1. That is, the question is ax raised to the power of n, and we're integrating now. So you add power and you add 1 to that power. So it becomes ax raised to the power n plus 1 all over n plus 1. That is, you are dividing through by the power. Then you put in the arbitrary value there, which is c. So that is how to go about the general form of this polynomial function. So let's now go on and look at another example on this. Now look at this example 1, where we have to integrate x raised to the power 3 plus 3x squared minus 4x plus 6. This is a polynomial function given here. So we have to integrate it now. So how do we go about it? We integrate x raised to the power 3. Then we have it as x raised to the power 3 plus 1 all over 3 plus 1. That is for the first function there. And the next one, which is 3x raised to the power 2. Let's now integrate it. We have it as 3x raised to the power 2. Then we add 1 to that power. That is raised to the power 2 plus 1 all over 2 plus 1. So Also 4s, you add 1 to the power, which is 1 plus 1 all over 1 plus 1. And the constant c, it is like you are having it as 6s raised to power 0 plus 1. So that is how to go about the integration. Now we now solve further to get the final answer as s raised to power 4 over 4 plus s raised to power 3 minus 2s raised to power 2 plus 6s and plus the sign of our constant, which is c. So that is for example 1. That is number 1 example under the polynomial functions there. Then number 2, another question there, we are to integrate s raised to power 4 minus 3s raised to power 3 plus x squared all over x in brackets the s. So now, for us to integrate this, so we first of all separate the values. That is, you make each function there all over that s, that is the denominator there. So we now have it as s raised to power 4 all over s minus 3s raised to power 3 over s plus s raised to power 2 all over s. We are still saying the same thing, because by the time you take the LCM of this now, it becomes the initial functions given. So we are still saying the same thing. Now we now want to integrate this. Now why do we have to split it in this form? Because for us to be able to integrate it easily. So by the time you're having it like this, you will see that the s at the denominator will cancel 1 s at the numerator. It will cancel 1 s out at the numerator there. So we now have integral s raised to power 3 minus 3s squared plus s in bracket the s. So that is the function now we are going to integrate. You will see that we can easily integrate this now. Then if we integrate s raised to power 3, it gives us s raised to power 4 over 4. If we integrate s raised to power 2, it gives us 3s raised to power 3 all over 3. And if we integrate x, it will give us s squared all over 2 plus the arbitrary constants. So that is the answer to that. We can leave the answer like that, and we can also have it in this form. We can also, we are still saying the same thing. Now we are done with the integration of a polynomial. Now we now want to move into integration of this rational function, that is this form where we have f prime of s all over f of s. You can see that f prime of s is the derivative of this f of s. The numerator is f prime of s, while the denominator is f of s. What are we saying here? That is, if you differentiate the denominator here, we are having the numerator. So that is the outcome of what we're saying here. Now, in trying to evaluate this now, let's look at this question where we have we are to integrate 1 all over s ds. Integrate, or we should compute integral of 1 over s ds. How do we go about it? Let's try this the method. Let's integrate straight away here. We have it as, you can write 1 over s as s raised to power minus 1. We are still saying the same thing. So if we integrate this now, it will give us s raised to power minus 1 plus 1 all over minus 1 plus 1. And it is s raised to power 0 all over 0. And this s raised to power 0 is 1 all over 0 plus c. It is infinity. That means it is undefined. Since it is undefined, then we now look into another method. We have another way of solving it. So since that method is not helpful because the result is undefined, however, thinking of integration as anti-differentiation. Now, since the method we first use is not helpful now, we now think of what to use again. We now apply the integration as what? As anti-differentiation. That is just the one we did in the previous section. So integration as anti-differentiation, let's look at it in that way. You know that 1 over s, ordinarily if you integrate 1 over s, it will give us what? Linear. It will give us linear. Now let's take the derivative for linear. The derivative for linear is also what? 1 over s. That is integration as anti-differentiation. If you have the derivative of linear, it will always give us 1 over s. And if we have the integral of 1 over s, it will give us linear. Now let's look at it in that way, following the principle that this is s in f of s equal to f prime of s all over f of s. Now see that since this s linear is equal to 1 over s, we can have that 1 over s ds is equal to what? D linear. What we just make we just cross multiply here for us to get to this stage. We cross multiply here, we have it as 1 over s ds and d linear. That is all what we did. At least we just take the s to go and meet 1 over s. That is the cross multiplication we did there. Now we now take the integral of both sides. Let's take the integral of both sides. We have it as integral of 1 over s ds equal to integral of d linear. So the answer will now give us what? By the time you take the integral of the linear, is going to give us linear, then plus c. So it is obvious that integral of 1 over s ds is equal to linear plus the arbitrary constant. So that is how to get that. Since the first method we used failed, so we have to move to think of another method to use. That's why we resolve by using what? Integration as anti-differentiation, and we got it in this way. Then if you integrate 1 over s, it will always give us s. Why? Even though if you differentiate the denominator, you know what is the denominator? The denominator there is x. Just as if how the function is given from here, where we have f prime of s all over f of s. That is, the derivative of the denominator will give you what you have at the numerator. So 1 over s here, you know, if you differentiate x, you are going to get what? You are going to get 1, because s raised if you differentiate s, you know, it is like you are multiplying 1 multiplied by s raised to power 1 minus 1, and s will be raised to power of 0, and anything raised to power of 0 is 1. So you see that the result you get when you differentiate the denominator is 1. And what are we having at the numerator? The numerator is also 1. So by the time you get that the value of when you differentiate the denominator and you get the answer as numerator, then you just take the length of the denominator. You take the length of the denominator. Therefore, you can see it here that by the time we differentiate the denominator, it becomes the value of a numerator. Then we take the length of the denominator, which is linear, because the denominator here is s. Then we take the length of it. Then it becomes a linear plus the arbitrary constant. So that's about that area. So we now move on. Now on a general note, integral f prime of s over f of s dx is equal to linear of s. So just like what we explained, that if you differentiate the denominator and you get the value of numerator, then you take the length of that denominator. That's the general note that that we're talking about here. So we can see that f prime of s now all over f of s ds is equal to ln f of s plus c. Now we want to look at this practical example again. Here we're looking at this example here. Now we have to evaluate integral of 4s plus 3 all over 2s squared plus 3s minus 1. 4s plus 3 all over 2s squared plus 3s minus 1 ds. Since it is clear that, look at it. Now we are taking the derivative of the denominator. What is the denominator here? It is 2s squared plus 3s minus 1. So let's now differentiate it. Let's differentiate it. By the time we differentiate it, you know the answer we got is what? 4s plus 3. And look at the value we are having at the numerator. You know it is 4s plus 3. So since we have the same answer as numerator, then we take the ln of the denominator. So that is what we're talking about. And this is the practical example of what we have been talking about. You take the ln of it. Since by the time you differentiate the numerator, then you are able to get the same value as the by the time you differentiate the denominator and you get your answer as that of numerator, then you take the ln of the denominator. So that is the answer here now. Now we take the ln, which is ln 2s squared plus 3s minus 1 plus c. So that is example on that. Now we look at number 2. We are given that integral of s plus 1 all over s squared plus 2s plus 1 ds. Now, how do we go about this? Now, let us look at it. Differentiate the denominator now. Differentiate the denominator. The denominator we are having here is s squared plus 2s plus 1. Let's now differentiate it. The answer we got is what? 2s plus 2. 2s plus 2. And looking at the numerator, you know, the numerator there, it is s plus 1. It is not 2s plus 2. So, how do we make it s plus 1 now? Then let's now take 2 out. Take 2 out from here. Then you know we have 2 into s plus 1. You know we are moving further. We have it as 2 into s plus 1. It is still not s plus 1. So how do we now proceed? Let's now proceed as follows. Now, since it is like that, you know, we can also have f plus 1 as 1 multiplied by s plus 1. We are still saying the same thing. If we multiply 1 by s plus 1, it's still the same thing. But what are we looking at? You know, by the time we differentiate the denominator, the answer we got is 2s plus 2. And we try to take 2 out, where we have 2 into s plus 1. Now, how are we now going to do it so that we can have exactly what we are looking for? Now, looking at it, it is 2 multiplied by s plus 1 and multiplied by half. If you multiply half by 2 by s plus 1, what do we have? You know that 2 can still also cancel out this half. Then you still have it as s plus 1. So, but from here now, since we are having it in this form, we are having it in this way, then you take that half outside. Take half outside the integral sign there. Take it out. We are left with 2 into s plus 1. Is that not so? So, since we are left with 2 into s plus 1 all over s squared plus 2s plus 1, then we now have our the next step as half integral 2s plus 2 all over s squared plus 2s plus 1, because if we still open that 2 into s plus 1, you still have the values as 2s plus 2, then all over s squared plus 2s plus 1 ds. So now, since we have done the necessary things now, we have done all the manipulation, we have arrived at half integral 2x plus 2 all over x squared plus 2x plus 1. Then you now take the lane of the denominator. We take the lane of the denominator. So since we have been able to do it in this way, because from where we have it as 1 over 2 multiplied by 2 multiplied by x plus 1, you know, it is the same thing as what? As the normal initial value given at the numerator. So we can easily have our answer as half ln x squared plus 2x plus 1 plus c. So that is how we arrive at that answer. So we now go on to integration of trigonometric function. Integration of trigonometric functions. Now we are going to look at this one with these examples. Integration of simple trigonometric function is easily understood from the perspective of anti-differentiation. So you can see that we are all this integration as anti-differentiation is very useful in this area. So looking at it in that way, for instance, number 1, we are to integrate sin s ds, which you all know that if you are integrating sin s, it gives us what? Minus cos s, then with the sign of the arbitrary constant there. So also, if we are to integrate cos s ds, you know, it gives us what? Sin s plus the what? The arbitrary constant. Those are straightforward but let's now look at how to integrate or evaluate tan s ds. Let's integrate tan s ds. So you all know that tan s is the same thing as what? Sin s all over cos s. I believe you all know that, but from our trig function, trigonometry, when we treated trigonometry in 101, tan s is equal to sin s all over cos s. Now, even from that of the one we did the other time, the previous example we did before now, you know, where we have f prime of x all over f of x, you know, from there, you know, we differentiate the denominator and we got what we have as numerator. We now want to use the same method now to solve this. Let's apply that method to solve this one. You know, let's make our cos s to be u. So by the time we differentiate it, we have it as minus what? Sin s. We have our du to be equal to minus sin s ds. So, but if you don't want to pass through all this, if you differentiate denominator directly, if we differentiate it directly, you know, we have it as sin s. So cos s, if we differentiate it, it will give us what? Minus sin s. And since we have arrived at the same value as that of the numerator, then you just take the ln of the denominator. But for you to be able to understand it better, let's represent the denominator here, which is cos s, as u. We now differentiate it. If we differentiate u, we have it as du over the s, du over the s. And if we differentiate it, it gives us what? Minus sin s. Then we make the u the subject of formula. If we make the u the subject of formula, it is equal to minus sin s ds. Minus sin s ds. Now, let's now go back to the question. We now substitute all this back to the question given, where we have our sin s is what? It gives us what? Du. Then the minus will be there. That is why the minus is outside the integral value. So we have it as u. Where we have cos s, it is u. Substitute it there. Then if we now want to integrate this, it will just give us as if we are having it as 1 over u du. And you know, just For example, the other one we did 1 over s. If you are taking you are integrating 1 over s, it is what? Ln s. And if you are integrating 1 over u, it will give us ln u. It will give us ln u. Then you put the sign of the sign we're having there, which is minus ln u plus the arbitrary constant. So what is u? From where we represent our u as what? Cos s. Then you now substitute back the value of u, which is cos x. Then you substitute back. It now gives us what? Minus ln cos s plus c. So that is just how to integrate tan s ds. So that is how to do that. Now we now move on to another example. Let's look at this one. This example where we have to evaluate integral of sine square s ds. Sine square s ds. So here we try to use the knowledge of trigonometry here, because you cannot directly integrate sine square s ds, because if you are to integrate it, you have to use the power reduction formula. And if you know the power reduction formula of what? Sine square s, you know it is 1 minus cos 2s over 2. But how do we arrive at that? How do we get that? So we now look at we use the knowledge of trigonometry. Then where we have cos 2s to be equal to cos s plus s. So we just have to solve this to get the reduction formula as 1 minus cos 2s all over 2. So all this, go through it step by step. Then cos 2s equal to cos s plus s, we have it as cos 2s. Which is equal to what? Is equal to what? Cos 2s will be equal to cos s minus sin s. So from that trig identity, so we know it, cos 2s will give us cos s minus sin s. Then we have it as cos square s minus sin square s. And what is the cos square s? Cos square s is always 1 minus sin square s. So that's why we have it like that. And 1 minus sin square s minus sin square s. So you know we are having 2 sin square s now. It becomes 1 minus 2 sin square s. And from here now, we want to make 2 sin square s the subject of formula. We take it out, we have it as 2 sin square s equal to 1 minus cos 2s. Then cos 2s has moved to the other side. So we have it in that way. We now have it as sin square s. At least we divide both sides through by 2. So we have it as sin square s equal to 1 minus cos 2s all over 2. So all this is just how to get the power reduction formula, because how do you know that sin square s is equal to 1 minus cos 2s all over 2? That is all just we did here to make you understand how we got sin square s equal to 1 minus cos 2s. Ordinarily, if I want to solve integral sin square s ds for you, I will just apply the power reduction formula. I'll just bring it out and write it as sin square s is equal to 1 minus cos 2s all over 2. But for you to understand how we got it, that is why we went through these all these steps to arrive at the power reduction formula. Now, since we have got it in this way, then sin square s will be equal to what? You know, we just separate it. We have it as 1 over 2, then minus cos 2s over 2. You can have it as 1 over 2 minus cos 2s over 2. If it is cos 2s over 2 or 1 over 2 cos 2s, we are still saying the same thing. So now we perform the integration. As it is now, you will see that you can easily perform the integration here. You can easily get it. You can easily get it easily. So now we move on. Now let's now integrate it. Integrate 1 over 2 minus 1 over 2 cos 2s. Then we can can do it straight away, or we can separate it also in this form where we have integral 1 over 2 ds minus, then we take the coefficient out here where we have 1 over 2 cos 2s. The 1 over 2, there is the coefficient of that of cos 2s. If you take it out, we have it as integral cos 2s ds. Now, if you want to integrate the constant half, that is 1 over 2 ds. If we want to integrate it, it is like 1 over 2 s raised to power what? 0 plus 1 all over 0 plus 1. We have it as 1 over 2s. And minus, this one is a multiplication. Then that's why we have the coefficient outside. Then you have the 1 over 2 multiplied by. Now, you are integrating cos 2s. If you are integrating cos 2s, it gives us what? Sin 2s all over 2. If you are integrating cos 2s, it will give us what? Sin 2s all over 2. So that's why we are multiplying this one together, and it becomes so 1 over 2s minus, we have multiplied by half sin 2s will give us 1 over 4 sin 2s plus c. So you can have your answer in this way. You can as well have it as s all over 2 minus sin 2s all over 4 plus c. So that is the way to go about this, and I believe it is very, very clear. So now we move on to integration by substitution. Integration by substitution. Sometimes, in order to integrate certain functions, we have to make substitution. Yes. Such substitution can be algebraic or trigonometry. It can be algebraic or what? Trigonometry. In algebraic substitution, we replace an expression with an alphabet. We replace an expression with what? With an alphabet. And when we are having an algebraic substitution, then we try as much as possible to express it with a what? With an alphabet. On the other hand, an alphabet is replaced with a trigonometry ratio when we perform trigonometry substitution. You can see that an alphabet is replaced with a trigonometric ratio when we perform trigonometry substitution. Now, algebraic function. In algebraic substitution, we replace the variable of integration by a function of a new variable. A change in the variable on the integration often reduces an integrand to an easier integrable form. Now, let's now look at all what we'll be saying now in these examples. Let's look at it. Now, we want to evaluate integral 9s plus 2 raised to the power of 6 dx. 9s plus 2 raised to the power of 6 ds. You can see that this is an algebraic function here. So look at it. We cannot just go about it. If we are to integrate this now, it will take long steps if you are using the direct integration. Now we now represent the value of 9s plus 2 as what? As p. We take p to be equal to what? 9s plus 2. 9s plus 2. 9s plus 2 is the one that is raising to the power of 6. That is those values in brackets. We raise everything to the power of 6. But we just take the one inside the bracket now and we represent it as p. We represent it as p. If we can get in the explanation very well, that is what's already explained. So now, we now take p to be equal to 9s plus 2, such that, what are we going to do here? We are differentiating. Let's now differentiating the p with respect, differentiating p with respect to what? To x. That's why we're having it as the p over the s. The p over the s. That is, you are differentiating the function there, 9s plus 2. So if we differentiate it, then the p ds will give us what? Will be equal to 9. The p ds will be equal to 9. That is, if we differentiate 9s, you have it as 9. But if you differentiate a constant, it will give you 0. So the answer there is equal to 9. That is, the PDS is equal to 9. Now we want to make our DS the subject of the formula. Let's now make the S the subject of formula. So we cross multiply. You know, if you cross multiply, it is like you are having it as the P equal to 9ds. The P equal to 9ds, but we are making the S the subject of formula. So it becomes the S equal to the P all over 9, equal to the P all over 9. Now let's go on. Now here we now go back to the question now. You know, we represent 9s plus 2 as what? As P. You now substitute back to that question given. So what is 9s plus 2? We represent it as P. Go and write P there. Where you see 9s plus 2, put P there because we take it as P. Then what is it raising? It is raising to power of 6. Then that P will now become raised to power 6. It becomes raised to power 6. P raised to power 6. And what is the S? The S here is what? Is the P all over 9, because we have our DS equal to the P all over 9. So we now, instead of writing the S again, we just put the value of the S there, which is the P all over 9. We write it there. So we now have integral P raised to power 6, the P over 9. So looking at this now, we see that 1 over 9 is the coefficient there. We now take it out. We take 1 over 9 as the coefficient. We take it out of the integral sign. Then we are left with what? P raised to power 6 the P. We are left with P raised to power 6 the P. So now you can see that we can easily integrate this now. You know, we are integrating P raised to power 6 with respect to P. So now let's integrate it. We have it as 1 over 9 into what? P raised to power 6 plus 1 all over 6 plus 1. Then it becomes P raised to power 7 all over 7. Then you add the arbitrary constant there. Now we have it as 1 all over 63 P raised to power 7 plus C, because if you use 1 over 9 to open that bracket, 1 multiplied by P raised to power 7 will give us P raised to power 7. Then if you multiply 9 by 7, it is going to give us 63. So it is now P raised to power 7 all over 63 plus C, or you have it as 1 all over 63 P raised to power 7 plus C. Then what is P? What is P? From where we represent P as what? 9s plus 2. So you now substitute back the value of P here. So we now have it as 1 all over 63 into 9s plus 2 raised to power 7 plus C. So that is the simplest way of getting this integration by what? By substitution. So that is all about that. I believe it is well clear. Now we now look into another example here where we have the trigonometric function here. We have the trigonometric function. We have to evaluate integral of sine raised to power 6x cos s ds. Sine raised to power 6x cos s ds. So here, how do we go about this? Just from that the explanation we made before, you see that we represent P. The alphabet P, we represent it to be equal to sine S. So now we are going to differentiate it now. We differentiate P. We now have it as the P ds equal to what? Cos S. So, you know, just like the way we handle the other one, you know, but this one is a trigonometric function. Then by the time we differentiate it, we have it as cos S. And we still want to make the S the subject of formula because we want to have values for that the S. So making the S the subject of formula, you cross multiply then you have the s equal to the p all over cos s, the p all over cos s. And the next step now, we have to substitute back to the functions given. The initial question we were given, we have to substitute all this back to the functions there. So we know that p is equal to sine s, and the s is equal to the p all over cos s. Where you see sine, that is, you put p there, sine s, just write p there, and you know it is raising to power of 6, then you put it as p raised to power 6, then multiply by, it is the sign of multiplication there. Where you see cos s, where you see cos s, write the cos s. Then where you see the s, what is the s from here? You have it as the p all over cos s, the p all over cos s. Then instead of writing the s again, you just write the p all over cos s. Looking at it critically here, you will see that cos s will cancel cos s there. Then cos s will just cancel out. Then you are left with integral p raised to power 6 dp. So that is the integral of p raised to power 6 dp. That is the original value functions we have now. So here now you can easily integrate. You can easily integrate from here. So we have it as p raised to power 6 dp. Then you integrate it, it becomes p raised to power 7 all over 7, then plus the arbitrary constant, which is c. Now here we will see that 1 over 7 is what? Is the coefficient there. Then we have p raised to power 7. What is p? P is sin s. You just substitute back the value of p, which is sin s. Substitute back, then we have it as 1 over 7 sin s raised to power of 7 plus the arbitrary constant. And you can still also have it as sin s raised to power 7 plus c all over 7. So just whichever way you want to leave your answer. So that is that about the integration by what? By substitution. So we now go on to the integration by parts. Integration by parts. Please, I want every one of you to listen to this very well. Now, occasions arise when we have to integrate the product of two functions, and the techniques we have learned so far may not be applicable. Listen, occasions arise when we have to integrate the product of two functions, and the techniques we have learned so far may not be applicable. In such cases, we can integrate by parts. That is all the methods we've been using before, and if you look at it and it is not applicable, then we now introduce the integration by parts. The formula for integration by parts arises from the product rule. I believe you all know what is called product rule. You know it. That is from the product rule techniques in differential calculus as follows. So we now look at it in this form. Given y equal to uv now, that is, given y equal to uv, if you want to have the product rule of this now, you have it as what? You know, y is the same thing as y of s, u is the same thing as u of s, and v is the same thing as what? V of s. Now let's have the derivative of it now. Let's differentiate it. We have dy dx equal to, that is from the product rule, then will be what? U dv over ds plus v du ds. I believe you all know that, which is the product rule. Now, multiply through by dx. We now want to multiply through, that is both sides, by what? Ds. We can progress as follows. We progress as follows. If we multiply through by ds, you know, ds will cancel out the denominator there. Then we now have the y equal to u dv plus v du. So that is what we are having. Now we now take the integral of it, of both sides. Take the integral of that integral dy equal to integral of the y equal to integral of u dv plus integral of what? V du. So that is that. Then we now move on. We now have integral of the y, we have it as y equal to what? Integral u dv plus integral v du. So from here now, we want to make u dv the subject of formula, u dv the subject of formula, take it out, then we now have it as integral of u dv equal to, that is, you know, while I've come to the other side, then what is our y from the question? Y is equal to uv. Then we, instead of writing y again, we now replace it as uv. You know, y is equal to uv right from the beginning. So they now have it as integral u dv equal to uv minus integral v du. So that is the formula for integration by parts. You know, this was derived from the knowledge of what? That of product rule technique. So that is the formula for integration by part. Please note it very well. Any equation or any functions given, any question or function given in this form, and then you are going to apply the integration by parts. Maybe you have used all other methods and you know it is not applicable, then we move on by using the method of integration by parts. Now look at this example. In order to evaluate, that is, we have I equal to integral s squared sin s ds. I is equal to integral of what? S squared sin s ds. Now, from the formula, we have, looking at it, integral u dv is what we are having here as integral s squared sin s ds. Is that okay? Integral s squared sin s. Then you are going to represent u as what? As sk and dv as sin s. That is all what we're saying here. Just relate the question with the formula here. We now have it as integral u dv is what we are having as integral s squared sin s. Integral of what? S squared sin s. So looking at it critically, you will see that u is the same thing as s squared and dv is the same thing as what? Sin s. U is s squared while dv is sin s. Now we are solving now. We are getting the solution now. We take u to be equal to what? S squared. That is, that u, we now differentiate it with respect to s. If we differentiate it with respect to s, we have it as du over ds, which is equal to what? 2s. Then we make the u the subject of formula. We make the u the subject of formula. If we make the u the subject of formula, it becomes the u equal to 2s ds. 2s ds. And you know, we represent sin s as what? Dv. Dv now is equal to sin s ds. Now if we integrate this dv, it becomes what? V. Then if we integrate sin s, it's what? It is minus cos s, then with the arbitrary constant. So all this now, you know, we have gotten our u as s squared, we got our du as 2s ds, and we got the v as sin s ds, and we got v as what? Minus cos s. Now we now want to substitute back to the formula of that of integration by parts. You know, the formula we derived there is integral u dv equal to uv minus integral v du. You now substitute all this back to the formula now. You know that the question is in form of integral u dv. You know that, which is s squared sin s dx, and it's the one we are going to look into now. We now represent it as I here. All what we are having as integral of s squared sin s dx is our I, right from the question. You know, I is given as what? Integral s squared sin s dx. So we represent it as I, which is equal to the formula now, uv minus integral v du. I equal to uv minus integral v du. Now, where you have u, substitute s squared there. You know, we have u as equal to what? S squared. Substitute s squared where you see u. Then what is v? Our v is what? Minus cos s. Substitute it back as v. That is why we have it as s squared into minus cos s minus that integral. Put it. What is v? V is also minus cos s, and you know the sign of multiplication there. Write it. And what is du? What is our du there? It is 2s ds. 2s ds. Substitute. Then we have it as 2s ds. So we now solve. Use s squared to open this bracket. We have it as minus s squared cos s. Minus s cos s. Now, the next one is what? You know, the integral there, it is minus integral into minus cos s multiplied by 2s ds. If we do the multiplication here, the minus minus will become plus. That is why we have it as, it will become 2s cos s ds. 2s cos s ds. Then we now take the 2 outside. We take the 2 outside the integral sign. Then we are left with what? S cos s ds. S cos s ds. And looking at this answer we got here, you know, we still have integral of what? Products of trigonometry there. One is for trigonometry, and one is what? Algebra. So we now have the product of it there. So what do we do again? We can't leave our answer in that form. Then we still solve further. We solve further. Now, instead of putting it as I again, we have it as I2. That is integral s cos s ds. We represent it as what? I1. That is, you know, 2 is after integral there. Then you have it as 2I1. For you to be able to differentiate it from the first I. You know, the first I, that is the question given from the initial stage. And now we have another question now we want to solve. Since we cannot leave the answer in this form, we still solve further, because you still have the product of two functions there where we have s cos s. Then that s cos s, integral of s cos s now, we represent it as what? I1. So we now want to solve our I1 now. And what is I1? I1 is what? Integral s cos s ds. So since we cannot integrate it directly, we now repeat the same process. We repeat the same process just the way we did the first one. Then we are going to apply the same method now, the same process with this. So let's now continue. Now, you know that what we are having as I1 is s cos s ds. Now, what is our s? What are we representing s with? From the formula, you know the formula is integral u dv equal to uv minus integral v du. That is the formula. Now we now make s with we represent u as s, and also we now differentiate it. If we differentiate it u with respect to s, we have it as what? As 1. You know, if we differentiate it, it's 1. Then we now make the u the subject of formula, and if we make the u the subject of formula, is equal to what? The s. And what is the v? The v is cos s, cos s ds. The v is cos s ds. That is, if we integrate the v, we have v. If we integrate cos s ds, we have it as what? Sin s plus c, sin s plus c. So here now, we've already gotten all this now. Then we now go and substitute back. We now substitute back. Where you see u, you substitute s. Where you see v, you substitute sin s. Where you see the u, then you substitute what? The s. So all this we now substitute back to we're using the same formula. Since we cannot integrate I directly, then we repeat that integration by parts again. Now we now have our u as s, put s. What is v? V is sin s, write it, minus the integral sign. What is v? V is sin s. And what is the u? The u is what? Is equal to the s. Then instead of writing the u, you put the s there. So let's now look at it. We see that s sin s there, then minus, if we integrate this one now, it is not a product of anything again now. We just have it as integral of sin s ds. Here we can easily integrate sin s. We can integrate sin s. If we integrate sin s, it gives us what? Cos s. So that's why we have our I1 to be equal to s sin s minus cos s plus the arbitrary constant. So we now have this now, since it is sin s, if we integrate sin s, it gives us what? Minus cos s. Yes, if we integrate sin s, it gives us minus cos s. So that is why this minus will become so positive here. Then we have it as s sin s plus cos s plus c. So now we now go back to the other one, where we represent that one by star. Then we represent the I1. I is represented by star. Then I1 is represented by star. Now we want to substitute equation star into equation star from the previous slide. Let's now substitute back. I is equal to minus s squared cos s plus 2i1. So I1 here is s sin s plus cos s plus c. So we now substitute back to where we have I1. Then since we have gotten the I1 as s sin s plus cos s plus c, we substitute back. Then we now have our answer to be what? I equal to minus s squared cos s plus 2s sin s plus 2 cos s plus, both are having constants. Both I and I1, they are having the arbitrary constant, that is why we are having it as plus 2c. Since it is c plus c, we have it as 2c. Then at the final stage there, we represent that 2c to be what? D, just for us to have a constant there. So we represent that 2c as d. So you can see the final answer as I equal to minus s squared cos s plus 2s sin s plus cos s plus d. So that is all about integration by parts, until you get to the final stage where you can easily integrate the last function, where you can easily integrate it, because it is not involving any product again. Then you can easily integrate. Since you can get that, then you can have the final answer. Or at times you may be given any question where you have the final, when you get to the final stage, and you can see that integral you get is the same thing as the initial function. Then you just have a way of rearranging the equation. Then you get your final answer. So that is all about integration by parts. So when next we meet, we will still have another example on this integration by parts for us to be able to understand just the one I just explained, and so that you can have at least like two example under the integration by parts. So I think we've been able to work on the methods of integration today. Thank you. This is where we're going to end the class. Thanks for listening. Bye for now.